I want to start with 2, actually. So is the random variable given in the company table discrete or continuous? Well, there's only 5 values for x. So it's discrete in the sense that it's finite. The other thing you got to do is make sure these add up to 1 and that they're all valid probabilities. They're all between 0 and 1 inclusive. So yes, I can do a quick add up and you can see you get 8. 8 and 3 is 1. Is 11, so 1 and 12, 19, 30, 3, 7, 1. So I get 1,001. So it adds up approximately to 1 because there's a round off. We can live with that. So it's a valid probability table because of all those things. So the random variable given is discrete mainly because there's a finite number. That's the bottom line. We're also going to point out that these will have to be numerical. We can't have a nominal, like gender or true false. It has to be numerical data. I mean, there's times when you can do those kind of distributions, but they're not what we're going to study. So the main thing here is that it has a finite number of, let's go back to 1. The table on the right consists of probabilities corresponding to girls. So it's exactly the table I wrote over there, only it's in decimal form. And because it's symmetrical, girls and boys are 50-50, so it's symmetrical. The probabilities doesn't change. So which is the random variable? What are its possible values? And are its values numerical? So the random variable is x, the number of girls in 3 births. The possible values are 0, 1, 2, and 3, and the values of the random variable are not numerical, so that one's not right. It's C, because they are numerical. So C is the right answer. So that's what we're looking for. We're looking for a finite number of values that are numerical and that the probabilities are valid probability distributions in the sense that there's nothing greater than 1, there's no negatives, and they add up to 1. So that fits the bill. They'll probably try to trick us a couple of times, but in the long run, we're really interested in ones that work. Yes.
I know we'll probably go back to another lesson, but for the negative part, what if there's a positive that equals out that negative and still adds up to 1?
You can't have a negative. Can't have a negative probability.
I was going to say, I thought that related to something.
As soon as you see a negative number, you just say that's not a valid probability.
Okay.
Now, the numerical values can be negative.
Okay.
Right now, we're doing examples that we already saw, and these are all numerical and they're all positive because that's the value that x takes on because there's 3 kids and they only can be 0, 1, 2, or 3. But we're going to have random variables that could be negative. They could be greater, well, obviously greater than 1, but they could be negative because they're numerical values that you're putting probabilities on. So you'll see as we go. We'll get a couple of ideas of that. So here we're going to look at this is a repetition of discrete and continuous. So it says determine whether the following are continuous, discrete, or not a random variable. Is the distance a football travels in the air after being thrown discrete, continuous, or not a random? So what are we actually doing here? Are we counting, measuring, or neither? Measuring distance, so it's continuous. So this is just instead of calling it a continuous, what did we call it before? A continuous value or now we're calling it a random variable. Okay, is the usual mode of transportation for people in city A? The usual mode of transportation. So if you ask somebody their usual mode of transportation, is it continuous, discrete, or neither?
Is that continuous?
Usual mode. If somebody answers bus, taxi, car, walking, those aren't numerical.
So not a random?
It's not a random variable.
Okay.
That's,
You can make those.
yeah, you can put numbers on them if you want.
Because wouldn't the mode of transportation be X, and then,
No.
oh, because that would make it nominal.
Well, how are they, they're just nominal, they're just
Okay.
names. And even if you put numbers on them, they're still just names.
Correct. Okay.
Because you're not counting or measuring anything.
Okay.
The number of free throw attempts, discrete. You count the, it says, soon as it says number, attempts, you're counting,
Okay.
so it's discrete. The amount of rainfall, you count rainfall or measure rainfall, and is it numerical? Yes, it's continuous.
Yeah, well,
The height of normally randomly selected person. You measure height or count height, or neither. You measure, so it's continuous. Last one. The number of statistics students now doing homework. Dude, you count them or measure them or neither. You count, so it's discrete. See, when it says number, that means it's a count. As soon as you see that word, you know right away. All right, that's the one to be yours. Number 8. Okay. When conducting research on color blindness in males, the researcher forms random groups with 5 males in each group. The random variable is the number of males in the group who have a form of color blindness. Determine whether the probability distribution is given. Is it a valid probability distribution? Well, they're numerical because you're counting. And if you add these up, you get 15 and 5 is 20, 14, 20, 1,000. So you get 1,000. So it looks like to me that everything's fine. All the probabilities fit the description, proper description, and it's numerical and it's finite. So yes. Mm-hmm. And now they want us to find the mean. So the mean is mu. Remember that? Lowercase m. X bar is the statistic. This is the parameter. And we create what we call the expectation. Expectation is a function. The expectation of x, like for this one, is the sum of x's times the probability of x. So what you do is you just take these 4 products and and add them up, and that's your expected value. So,
which would be 1.
For this one, it would be 1.5.
Oh.
See what I'm saying is 0 times 1/8 plus 1 times 3/8 plus 2 times 3/8 plus 3 times 1/8.
Okay.
So you get, that's 0, so you get 3 plus 6 plus 3 is 12/8, which is 3/2, which is 1.5. That's the expected value. If you think about it, it's right in the middle, because half the area is on either side.
Okay.
So that's the mean.
Okay.
Well, it's the median. But in a symmetrical, here's what's nice about a symmetric. This is symmetrical. Do you see it as being symmetrical? This vertical line, it's the same on both sides if I folded it over. This is actually the mean, median, and mode. It's all 3 of them. That's what's nice about the normal distribution. This one here. This value in the middle, which is mu, is the mean, the median, and the mode. Or it could be x bar. Either one, depending on what you're doing. But this is how we calculate it. Now, you don't have to do this. I have to do, I could skip the first one, but I got to do 5 products. But guess what? Calculator will do it for me, or the computer. Now, here's how we do it. We open up the data in StatCrunch. And I go to Stat Calculator and Custom. We're going to be using binomial later today. We'll use normal and we might use the T also later on. So we're going to use custom T, normal, and binomial. Custom means you just take what you got, what they gave you. So yeah.
What would a gamma calculator?
That's just a type of distribution. That's a type of a continuous distribution. The hypergeometric these two are discrete. The normal and log normal are continuous. This is a discrete. This is a continuous. This could be either one. That's a continuous, discrete, obviously. Well, okay.
Yeah.
So this is continuous uniform. You got a discrete uniform.
Okay.
Chi-squared is a continuous. Cauchy is a continuous. Binomial is a discrete. The beta is a continuous. There's all kind of distributions. They give you all kind of curves and whatnot. So the ones that we're really interested in are the normal. But anyway, I want to do custom. So it asks me, what are the values? Well, the values are the x's. And it says weights. Weights means their probability. It's just another word for probability. And so I hit compute, and I don't get a histogram. I get a very weak box plot. It's real narrow. All it is lines. So the heights are the probabilities. This red one represents 0.663. See it? This one represents 0.282. See it? So these are the actual heights. So if I would have put boundaries on, I could make rectangles, and it would be like the one I drew there. So you can visualize that. They don't do it for us. But now notice they give us the mean and an S. This is mu and this is sigma. So they want to know mu to one decimal place, so it's 0.4. Okay? See, if I would have multiplied and added them up like I did there, that's what I would have got, 0.399. And then the sigma is 0.6 to one decimal place. I don't know why they just want one decimal place, but that's all they care about. Now later on, we're going to be using this for various calculators. If you wanted to know what's the probability that x, let's say, what's the probability x is greater than or equal to 2, you would just do this. And you would hit compute. And what it did, it added up all of these, all of those, and it tells me that it's 0.055, which you can see if you added those up. So you can have all these different, you can have less than or equal, greater than or equal, less than, greater than, or strictly equal. Now equals is easy because look, if I said equals to, there it is, 0.049. This repeats the data. So this is kind of neat. Plus you see, it highlights in red which one we're looking at. Okay? All right, so let's do number 9. Same idea here. First of all, is it a probability distribution? Well, it's numerical, it's finite, but doesn't add up to 1. So the sum of probability is not equal to 1. It's equal to 0.1.
It is,
yeah, see, that's the trick. You add those up and get a 100, and you go, oh yeah. But you're looking for 1,000 because it's 3 places. That's how I forget about the decimal. I just look at the numbers and add them up. Any questions? So, don't forget to answer this. See, if it's a no, so the table is not a probability distribution. You get 3 points this way. The table is not a probability distribution. See, because if you would have said yes on the top, and then they would expect you to put some numbers on the bottom, and they'd be all wet, so to speak. So be careful. Okay? Don't fall for it. Right. All right, number 12. Is it valid? Yeah, it looks like it. You can do a real quick add there. You'll see you'll get 1,000, and it's finite. It's numerical, so yes. Then they're going to ask us once again for the values. So We open it up in StatCrunch. We go to Stat Calculator Custom. And the X's are the values, the weights are the probabilities, compute. I like to open it up. See, the reason these are red right now, this is where it queues up. It's just, all we're looking for is these two numbers. But the mean, 1 decimal place would be 0.8. And the standard deviation for 1 decimal place would also be 0.8. See? Okay?
Does the mean and standard deviation in this sense have any correlation?
No. One's a measure of center and the other one's a measure of spread.
Okay.
We did use them when we talked about the coefficient of variation. That's creating another statistic.
Okay.
15. Refer to the accompanying table which describes the result from groups of 8 births from 8 different sets of parents. So I guess these 8 different sets of parents had 8 children. Wow. Big families. So we want to find the mean. So this is when we got to open it up twice. We got to open it up again in StatCrunch. Again, I don't need it anymore, so I'm going to close it and make this a little smaller and do Stat Calculator Custom. And the number of girls is the X and the weights is the probability. Compute. And you can see how symmetrical it is because the probability is 50-50. So the mean's 4, right? 1 decimal place, 4.0, yeah, 4.0. And the standard deviation is 1.4. So I'm going to use this to my advantage right now. I'm going to talk about the rule of thumb. What would be our expectation for the rule of thumb? Remember what it was? Mu plus or minus 2 sigma.
Okay.
So I'll use the calculator so you can see what I'm doing. So mu is 4. I'll do the lower end first. Minus 2 times 1.4. So on the lower end, it's 1.2. Then if I do second enter and do a plus sign, the upper end is 6.8. So 0 and 1 are not included, and neither are 7 and 8. You see that?
So it's cut from what?
Because the data goes from 0 to 8. The confidence interval goes from 1.2 to 6.8. So I can't include 0 and 1 because they're both less than 1.2. I cannot include 7 and 8 because they're greater than 6.8. So my confidence interval won't include this. There's my confidence interval. So these should be considered statistically significant. Let's see if that's true. If I do x greater or less than or equal to 2, 1. See, it's less than 5%. So 1 is significantly, and by symmetry, it's going to be the same if I did x greater than or equal to 7. If that includes 7 and 8, you see it's less than 5%. So that's kind of like, it's not quite 95, but it's close. That's my 95% confidence interval from 2 to 6. We're 95% confident, and what we're going to say is that the true mean is between 2 and 6. Right.
Which is 4.
Because that's what this sample's telling me, because we don't know where the true mean for us 8 kids is, but it's somewhere between 2 and 6.
So you can't cut them in half.
Right.
Okay.
It's discrete.
Okay.
But our measurements for setting off intervals can be decimals.
Okay.
It's just that we can't, it tells us where,
When you present.
it's kind of good in a way because we want a cutoff point that's not one of these numbers. So see our cutoff points here and here. So that creates our interval of confidence. Okay? So that's a use of that what did I call it? Rule of thumb.
Correct.
Yeah. Okay. So let's move up to 24. The table describes the random variable X number of adults in groups of 5 who reported sleepwalking. So we could put this in StatCrunch, or we could just answer the questions based on the table. Find the probability of getting exactly 4 sleepers among 5 adults. Well, there it is, 0.025. Right?
Right.
Let's just use the table. And then they want to know what's the probability of getting 4 or more. So I just add those two. 4 or more is 4 or 5. So 0.029. Right? Now they're going to ask us, which probability is relevant for determining whether 4 is a significantly high number of sleepwalkers? So we don't just look at equals 4, because 5 contains 4. So we have to look at the second answer, the one in part B. So since the probability, which one is it? Since the probability of getting 4 or more sleepwalkers is the probability of the given or more extreme result, part B, the second answer, is the one we want. We want the sum of 4 and 5. Because 5 contains 4. Correct. That's the whole logic. It took me a while to figure that out. So is 4 a significantly high number? We don't need that anymore. Remember, they're using 5%. So are we less than 5%? Yeah, we're at 2.9%. So since we're less than 5%, it's significant. So okay.
Okay.
I know it's you kind of think backwards, like you need to be significant, you need a big number, but it's a small number because you're in the tail. That's what's significant statistically. Okay. Number 27. Okay, now here's one where we're gonna do a random variable with strange numbers. In the state's pick 3 lottery game, you pay 96 cents to select a sequence of 3 digits using 0s to 9, such as 766. If you select the game sequence of 3 digits that are drawn, you win and collect $299.46. Okay, so how many different selections are possible?
Combination of 3.
You have three numbers to pick. How many choices do you get for the first number?
Combination of 10.
10. How many choices do you get for the second number?
10.
Third number?
10.
10 times 10 times 10 is? Right?
Yeah.
It's 0, 0, 0 to 999. That's the choices. So there's 1,000 choices. Right?
Do I want to do any combinations? Yeah.
No. Well, no, because you're repeating.
Okay. You
know,
the options available.
Yeah, well, I'm thinking like this. You got three choices. You got 10 times 10 times 10. if repetitions weren't allowed, then it'd be 10 times 9 times 8, which is
Okay.
10 pick 3.
Okay.
Yeah.
Okay.
You have to use the right counting technique given the scenario.
Okay.
All right, so there's 1,000 possibilities for selection. What's the probability of winning?
1 in 1,000.
1 in 1,000. As a decimal? 0.001. Okay. If you win, how much do you win? Notice it says net.
What do we collect?
Would you win $299.46?
Value minus 96 cents.
Minus 96 cents because you already paid. So you net $298.50.
There you go.
Follow?
Yeah.
What's the expected value? So you got to create a probability density function or distribution function. And guess what it is?
3.
There's only 2 values for x. The random variable takes on 2 values. You either win $298.50 and your probability is 0.001. Or you lose 96 cents. Notice the negative.
Mm.
And what's the probability of losing? Only one winning ticket. That means that 999 other tickets are losers. So if I multiply this times this and add it to the product of this times this, that's my expected value, because remember, the expected value of x is the sum of x times p of x. So it's just these 2 products added together. So I take 298.50 times 0.001, and I'm just going to put the minus here instead of adding. I'm going to subtract 0.999 times 0.96. So it's 60 minus 66, nearest penny. So minus 66 cents. Okay. Now, whose perspective is this from? It's from the player, because it says you pick. If I could turn this around, if I turned it around, what would be the distribution from the term? How would I change this if this was in terms from the lottery exchange? This would be minus and this would be plus, because they get 96 cents for every ticket that doesn't win, and they got to pay out $298.50 for every ticket that loses. So for them, the expected value is plus 0.6. That means they're going to keep 66 cents of every ticket. See, if they sold all 1,000 tickets that were all different, right? They would lose 30 cents per ticket because they kept 66. What's 30 times 9.99? 30 cents times all the losing tickets. If they only sold one of each, see, there's your payout, roughly, because we rounded. And then they keep the rest. They keep the other $700 or so. All right. So the problem for them is if they have more than one winning ticket. Because people come in buy any ticket they want, and then they have other deals going on. But just if we didn't have any other games, extra games going on, it's just a straight up lottery with three numbers. If they sold one of each, they would make a very handsome profit. So that's the expected value. You can see it's from whose perspective. So from the perspective of the player, we came out with minus 0.66. That means that every time you buy a ticket, you can expect to lose 66 cents. Now, you don't get 30 cents. It's just that the law of large numbers. If you played it a couple thousand times, you could expect to make 30 cents for each ticket you bought over the span of a lot of tickets. That's a law of large numbers. So there's a lot of people sitting around to figure out all this out.
So for,
Expectations and whatnot, and then they devise all these games. So
for the lottery, when they do the lottery, are they just throwing out like the Mega Millions or whatever, right? Are they throwing out this major number and hoping more tickets are bought than what it would cost for payout?
no, that builds up. They start at a place where there's no winners. Then that just builds.
And you know, anyway.
Because that's what happens.
Okay.
As soon as there's a winner, they default back to a starting point.
So if someone does win that initial.
Yeah, so like for 20 drawings, nobody won. That's 10 million every time. So now they're up to 200 million.
Okay.
You know, minus if they probably have some percent they keep for expenses. Okay. The last question is, if you bet 96 cents in the state's pick 4 game, this was pick 3 game, and the expected value is the same as we just had, which bet is better, the pick 3 or the pick 4?
Pick 3.
It doesn't matter. Your expected value is the same, so they're the same game.
But you have a higher profit.
Nah.
You're gonna have a higher probability.
No, the expected value is what you're interested in. Yeah. Now, when the expected value is 0, that's what we call a zero-sum game, which otherwise is known as a fair game. That means there's no advantage to any player,
Okay.
or either player or any player.
Okay.
That's what you play when you're playing with your cousins and your in-laws. Because if you go to these places, these casinos that run these, you look around, where do you think they got the money to make them such an attractive place? That's the architecture is, you know, it all comes out of your wallet.
Oh.
Everybody's wallet that went in there, that's where the money came from. Because they keep a large percentage. You know what the game with the lowest expected value for the house is? The most fair game in Vegas. What is it?
Oh, it'd be roulette.
Right. That's right. Roulette has an expected value of minus 29 cents, I think. 0.2 on it. For every dollar, they keep 29 cents. So they're paying out 70 cents on the dollar. Every dollar runs across the table, they're putting back 70 cents in your pocket, but they're keeping 30. So other games, like, you know what the most unfair game is? It's the one that everybody plays when they're sitting around eating lunch. Yeah. I can't remember.
Slot?
No, well, slots are bad. Yeah, slots are bad, but there's a Tico or
The Chinese one?
something. Anyway. So let's look at the next one. Next one deals with insurance. There's a 0.9988 probability the randomly selected 33-year-old male lives through the year. A life insurance company charges $186 for ensuring that male will live through the year. That's premium. If the male does not survive the year, the policy pays out $90,000 as a death benefit. So, what's the value corresponding? There's two values here. There's a plus and a minus. What's the value corresponding to surviving the year? This is from the perspective of the person being insured.
0.9988
No, that's a probability.
of them surviving the year.
We want the random variable.
One.
No, we want the value corresponding to surviving the year. It's dollar sign. It's the money. It's money.
Okay. So it would be their, yeah, it would be their,
well, it's not quite right. It's only half right. You need a minus.
because you pay it.
That's what it's going to cost him to live the year. I mean, it's going to cost him, even if he dies, it costs him, because this one is going to be 90,000 minus that. So it's 89, 814. I subtracted 186 from 90,000. See that? Remember I told you 9s and the last one's a 10?
Yeah.
See, 8 and 1, 1 and 8, 4 and 6. Okay, so those are the two numbers that are the random variables. Okay, so the expected value. So let's do it a different way this time, okay? Just so you can see that you can, if you want, you could do it this way. Oops. I could just create my own input. I could put in minus 186 for the first one and 89,814 for the second one. And in the second column, I'll put probability. I could even change them. I could even change these if you want. You could rename the column. You could call it or you can call this probability. Okay, so what's the probability of living through the whole year? 0.9988. So what's the probability of meeting your demise? 0.0012. Right?
Wouldn't you need ones in the first two columns?
Add those two numbers up. What do you get?
I don't want to know. I don't want to add them up.
Oh, come on. 88 and 12 is 100. And 100 plus 99 is 100. So you get your one. Look, I'm 12 away from being all zeros. Look.
Yeah, okay.
Forget about the decimals. Just look at the numbers. It's real easy to do. Okay, so now what do? Watch. I go to Stat Calculator Custom, and I tell it the values are in the payout and the weights are in the probability, and I go compute, and see, there's my mean, minus 78. So that's my answer, minus 78. So what this means is that the company's going to keep $78, a profit of $78 from each policy.
If they die?
No. I said they're going to make a profit of $78 from each policy.
So if they don't.
That's what the company's going to keep, because that's what you're losing.
Okay.
In other words, the company gets $78 of each 186. The remainder is 108. That's what goes toward the death benefit for whoever dies. Okay. So think about this logically. Let's think about it logically. What's that?
It's like a savings account. You're paying them money and they keep their holdings.
Yeah, but you got to pass away. See, 108. I'm just going to say there's 1,000, right? Let's say there's 1,000. If I do that times 99, see there. I'm sorry, 999. 108. I don't know why I did 99. 108 times 999. Let's just say there's 1,000. See, there's my 90,000 essentially. Follow? Yeah. So if they could sell 1,000 policies, only one person dies, then they make a profit. The thing of it is they have to sell a lot more than 1,000 because there may be more than one person dies. So can they make a profit? Yes, because the insurance company expects to pay an average profit of $78 on every 33-year-old male. Sure. See? Because don't forget, the expected value is from the insured's point of view. So the minus means that's what the insurance company's giving. Usually you go from the person that's paying. If you're working for a casino, you're going to turn it around. You're going to tell your bosses, yeah, you see that expected value is 78. We can expect to keep $78 of every. You know what I mean? It all depends on who you're doing the accounting for. Yeah. All right? So you can see that how the expected value is useful. All right, so guess what? That's it for this section. We're going to go to the specific binomial. So let me tell you about the binomial. It's on here. I'll bring it up here. You can look at it. It's on the back side. It's a discrete probability distribution for an experiment procedure consisting of a succession of trials such that the number of trials is fixed. That's N. The trials are independent. That means the probability doesn't change. There are only two possible outcomes, success, failure. And the probability P remains the same. So that's the same as saying they're independent.
And, okay, those.
So notation, I'm sorry?
That's what defines it, right? The 1 through 4?
Yeah.
Okay.
That's what we gotta have.
Okay.
And then the notation, S and F, success and failure. The thing of it is here, now, this is statistical success. Like, if the experiment is somebody has cancer or not, you know, a person that has cancer is a success. Go figure. Statistical success doesn't mean they're social success. The probability, little p, is the probability of a success. So you only need two parameters for this distribution. You need n and you need p. That's it. Q is 1 minus p. Q is the probability of a failure. P plus Q equals 1. Because there's only two outcomes. So for any experiment, you either have P or probability P for success, probability of Q for failure. And they have to add the 1 for any particular trial. N is the total number of trials. X is the random variable. X takes on the value of the number of successes from 0 to n. So there's n plus 1 possibilities. If you have 10 trials, there's 11, X goes from 0 to 10. So there's 11 numbers in the probability density distribution. P of X is the probability. This is the formula, which we'll generate. We'll show you. We'll show you where that comes from. So, with that in mind, and you have it on the printout for yourself, let's go ahead. No, I'll wait. Go ahead. Doing okay? Okay, so you can, I would refer to your handout for binomial as we go, so you can, because it's going to be difficult to remember some of this if you haven't seen it. Okay, based on a survey, assume 45% of consumers are comfortable having drones deliver their purchases. That's P. That's the probability of a success, considering the success is that they are comfortable having drones. Suppose we want to find the probability that when 6 consumers are randomly selected, exactly 2 of them are comfortable with delivery by drones. They want us to identify N, X, P, and Q. So what's the value of N? How many trials is it? 6 consumers. And then what's the number of successes?
4 or 2 of them.
2. Exactly 2 are comfortable, so that's X. Remember, X goes between 0 and 6 now. It could be any number between 0 and 6. And then what's P? I think I gave it away. 0.45. And what's Q? P plus Q equals?
P probability of failure.
Well, Q equals 1 minus P. That's the other way to look at it. So what's 1 minus 0.45?
It'd be 55.
0.55. Right, you got it. 55 and 45 is 100. That gives you your 1.00. All right, let's go back to number 1. Here's where we're going to generate the formula for the binomial. Okay, based on a survey, assuming 59% of consumers are comfortable having drones deliver their purchases. Suppose we want to find the probability that when 6 consumers are randomly selected, exactly 4 of them are comfortable. What is wrong with using the multiplication rule to find the probability of getting 4 consumers that are comfortable with drones followed by 2 consumers not comfortable, as in this calculation? Would the correct answer be 0.0204? Something tells me that's not correct. Here's 1, 2, 3, 4 successes and 2 failures.
Yeah. So what is wrong with?
What's wrong with that?
So you'd be adding the failures into the. You only have 2. You have success.
Yeah, there's 2 failures.
Yeah, but I'm saying you have success and failures. You can't have the failures within the successes.
No. See, this is the tree diagram.
Okay.
Success, failure.
But that, okay, so that one right there is just multiplying. You have to minus the failures from the success.
No, there's no minus. There's no minus. The problem is they went on this one branch. There's going to be 2 to the 6th, which is 64. There's 64 branches. They only chose the one branch that had 4 successes and then 2 failures. Is that necessarily how they occur all the time?
No.
They could have 2 failures first and then 4 successes.
Okay, I see what you're saying.
So the order is specific to having just one ordering.
Okay.
That's the problem. The probabilities are correct because success is 0.59, so failure is 0.41 because they have to add up to 1. So that's no problem. The problem is that there's more ways. Let's see which one. There's other arrangements. That's the problem. Okay. So the formula turns out to be you will have P to the 4th Q squared because you will have four successes and 2 failures. But then you need C 6 choose 2 because you can have 6 that many different groupings. You have that many ways to choose them, right? If there's six trials, I'm sorry, 4. You choose 6. You have 6 choose 4 different ways. Out of those 64 branches, let's see what that is. That's 6 factorial over 4 factorial, 2 factorial. C 6 choose 4. So the 4 factorial cancels, so that's 6 times 5 over 1 times 2. There's 15 different branches. There's 15 different ways to arrange those. So that's where the formula comes from below. Okay? So I wanted to point that out to you. And now they're going to run us through an example of that, I think. Number. Oh, okay. This one's interesting also. A Gallup poll of 1236 adults shows that 12% of the respondents believe it's bad luck to walk under a ladder. So that's P. Consider the probability that among 30 randomly selected people, so they're going to select 30, so that's N, 30 trials. And there's at least 2 that have the belief. So we want the probability X is greater than or equal to 2. X could be anywhere from 0 to 30. We want the probability X is greater than or equal to 2. So, given that the surveys were selected without replacement, the events are not independent. Can the probability be found by using the binomial probability formula?
No.
Well, no, because they're not independent. However, is 30 less than 5% of 1236? Yes. So we can assume independence because the sample is less than 5% of the population. So that allows us to say yes. So although the selections are not independent, they can be treated as independent by applying the 5% guideline. Remember that one?
Mm. So
this is a case where we can do that. All right? Yeah. Number 6. They want us to ask us if this is a binomial distribution. So we have to have those 4 things. The Y-sort method of sex selection developed by Genetics Institute was designed to increase the likelihood that a baby will be a boy. 20 couples used Y-sort, so that's N. The method gave birth to 20 babies. The sex of the babies is recorded. Well, the probability is constant because it's 50-50. And there's a set number of trials. There's 20 couples. There's 20 trials. And the trials are independent because the birth of one child does not affect the birth of another child in another family. And there's only 2 outcomes, either a boy or a girl. So a boy would be a success. A girl would be a failure, not statistically. So yes. It's a valid binomial. See how much we read into that?
Mm.
Okay. Number 10. Oh, that's it. Okay, this one says 8. Same idea. Is it a valid binomial? 8 different senators from the current U.S. Congress are randomly selected without replacement, and whether or not they serve over 2 terms is reported. Well, the problem is they're not independent. So we got to look at the sample size. It's 8, and how many senators are in Congress?
Or is it 100?
100, 2 for each state.
Yeah.
You agree? It's 100 senators. And 8 out of 100 is what percent?
8.
So it's greater than 5%. So
Correct.
you can't assume independence. So that the trials are not independent. See how this time failed? We can't do it. We can't use it as a binomial. We can figure out some other way to do it, but not as a binomial. Number 13. I think we're going to get into calculating. Okay. Here's an example of how we would calculate. So multiple choice questions have 5 possible answers, A through E, one of which is correct. So assume that you guess. 3 questions. So N is 3. Use the multiplication to find the one branch, CCW. Correct, wrong. Okay. So getting it correct, what's the probability that I got it correct? 1 out of 5. Times 1 out of 5. And the probability I got it wrong? 4 out of 5, because they have to add up to 1. So I have 1 times 4 divided by 5 cubed, so it's 4 over 125.
Where do you get a 5 cubed?
Okay, I'll show you the tree. See, I'm telling you, if you draw tree diagrams, you're ahead of the game. Correct, wrong, correct, wrong, correct, wrong, correct, wrong, correct, wrong, correct, wrong, correct, wrong. So we have CCWs. So it's the branch that we're looking at is right here. This times this times this. So we said this is 1/5, 1/5, and this is 4/5. So you multiply. You get 4 over 125. Right?
Correct.
You can put it in as, it says exact answer. So we know the fraction, so let's just go ahead and put it in. Okay, so what's the probability of CWC? So that would be CWC. It's the same exact probability, isn't it? It's just a different ordering.
Yeah. So
before, let's this time let's do it as a decimal, see if it works. 0.032. And the last one we'll do as a fraction again. It's the same thing, right? WCC.
They're all the same.
Yeah, WCC. 4/5, 1/5, 1/5. Those are the 3 branches that have 2 correct. Right? This is just like boys and girls, only instead of being 50-50, it's 1/5, 4/5. But when you have only 2 outcomes for each of 3 trials, you have 8 total branches. Just like you have for boys and girls, only the probabilities are different. Right? Same tree. All right, so 4, let me put 4 over 25. I just wanted to show you, you can do decimals or fractions as long as it's exact, which means if you don't have a terminating decimal, you can't use it. Like if this were 0.333333, then you couldn't use it.
Okay.
But you'd have to use 1/3 as a fraction. Unless they told you could round.
Right.
But you see, they say here, type an exact answer. So that means it's either terminating or the correct simplified fraction. So what's the on the basis of the results, what's the probability of getting two correct answers when 3 guesses are made? What do I do now?
You correct wrong. So it would be 4 out of 125.
Yeah, for this one. And for this one. And for this one. But they all give me 2 correct in 1 row. So what do I do with those? I add them up. That's right. I add up all the branches. Those are only 3 branches I'm looking at, so now it's 12 over 125. Right? Or 0.096. Either way. So what we did here, we found the probability that x equals 2, n is 3, x is 2, p is 0.2, q therefore is 0.8. So this will be c, 3 choose 2, 0.2 squared, and 0.8 to the first power. These 2 exponents add to n. And this is x. So 3 choose 2. How many ways does 3 choose 2?
3 ways.
Well, 3 factorial over 2 factorial, 1 factorial. 1 factorial doesn't mean anything, so it's 6 over 2 is 3. There's 3 different ways. There they are, 1, 2, 3. And this is 1/5, and that's 4/5. So we did it just piecewise, and I helped you by constructing the tree and showing you where the formula comes from. This one's squared. So you get 3 times 4 is 12, and you get 5 times 5 times 5. There's your answer. Exactly. Okay? So that's the formula. But you don't have to apply the formula. Just know that there is a formula. If somebody asks you about it, you say, oh, yeah, that's where it comes from. Because guess what? We're going to use the calculator or the computer. And here we go. Assume that the procedure yields a binomial distribution. I'll show you that. This is how we used to do it in the old days. You have a table in the back of the book, and you have P across the top, and it was 1.01, 0.05, and then by tens, and then 95, 99. And then N had, if N could take on value 0, 1, 2 for X, 3 could take on 0, 1, 2, 3. So you had all the values. These are the probabilities that X equals, for N equals 2, X equals 1, there it is, 0.095. By table. That's how we used to do it. Let's see if it's right. Oh, I might have taken the wrong, this says 0.10, I did 0.05. I did this column. So it's that 0.180. All right, so, but how would I do that by formula then?
Plug it in.
Well, you could just do it real quick, watch. What's it called? Well, just call it success, failure. And only ones that count are these middle ones, because these are two successes, those are two failures. We want probability of one success. So it's 0.1, 0.9, 0.9, 0.1. So when you multiply those, you get 0.09, 0.09, and when you add them together, you get 0.18 with a 0. See that? All right. Now, I've shown you a couple times by hand, no more. Now we're gonna use the calculator. So what I'm gonna do is open it up. I'll just leave it open because we're gonna need it for the rest of the way. So before we did custom, now we're gonna go binomial. The second one, binomial. And what you have to do is you have to put N and P. Remember I told you there's only two parameters, N and P? And then X takes on any value between 0 and 10, in this case. And once it knows P, it knows 2, because it knows how to subtract from 1. So it does automatically. So here, it says assume the random guesses for 6 multiple choice. So that's N equals 6. Oops, not 9, 6. And the probability of a success is 0.045. 0.045. And they want the probability of fewer than 4. So that's less than or equal to 3 or less than 4. Either way, you could do it. So less than 4 is 3210. So it's adding up all those 4 red ones, and it tells me that's the probability. 4 decimal places, 7447. So 07447. Okay? So let me show you what it would be like if I use stat disk. On stat disk, probability distributions, I go to binomial. I tell it number of trials is 6. Number of probability of success was 0.45. And then if I don't tell it what value X I'm looking for, it just gives me all of them. See there? It gives me all of them. It gives me all the individual values as the probability distribution, and then it gives me cumulative, going up and going down. See, X or fewer, X or greater. So we want X less than or equal to 3. There it is, 7447.
Okay.
Different style.
Okay.
There's so many statistical software packages, and they all do the same thing. All it has to know is N and P. Now, if I had a specific value of X that I wanted, I'd put it in there and it would just give me one row. And then look, I also get the mean and the standard deviation, which we got on ours also, mu and sigma. So they're all pretty much the same. They all help you as best they can. See, this one didn't give me mu and sigma. I take that back. We'd have to ask another way, I think. Oh, that's right. There's a shortcut for mu and sigma. Mu is just NP. So you just multiply 6 times 0.45, and that's mu, 2.7. And then sigma is the square root of NPQ. So you can calculate those. It's a shortcut formula because of the nature of the binomial. It doesn't. See, the calculations, I didn't show you the calculation for sigma. Actually, they give you sigma squared on the other side. It's a little more complicated. You don't have to do it because the computer does it. But for the binomial, sometimes you need to do it real quick. That's pretty simple. You got right here MP. So it's 240 plus 30 is 2.7. And then you need a calculator to calculate sigma because you need a square root. So, but here, let me show you what I would do is if I wanted n, I'd do 6 times 0.45, which is 2.7. And then for sigma, I do second square root. I already have NP, so it's 2.7, and then Q is 0.55. So 1.21. Isn't that what it showed us on the other? 1.22. All right, so you can see that shortcut. Real nice. Assume random guesses are made for, see, now I don't have to close this. All I got to do is go down here and change. As soon as I see n, there it is, 8. Multiple choice, P is 0.2. Five answers, so P is 0.2. And what's the probability of no correct answer? So that means X equals 0. Compute 0.168. Easy enough? So just remember, you have to put in the 2 parameters, n and p. And then here's your space where you can put a relationship between x and some number. You can have greater than or equal, less than or equal, equal. You can have greater than, less than, all those relationships. And then when you hit compute, it gives you a whole bunch of decimal places. When we get to the normal, we're going to always use 4 places. So it's not unusual for them to ask for 4 places. Here they only want 3. Just make sure you answer the way they want it. I'm giving you guys credit when I see your papers and you put too many decimal places. You got some more points on your test because of that. Right? I look for that. I'm not here to make you, that's not part of this class, but you should be doing that correctly because you're going to be working for somebody, you know, if they say 3 decimal places, don't give them 4. Don't give them 2.
I would want all, to be honest. I want to know the exact phrase.
All right, ready? Here we go.
Go for it.
Number 13. Assume that when adults with smartphones are randomly selected, 53% of them use them in meetings or classes. If 9 adults, you see right away, I know that's 9, n is 9, and I know p is 0.53. Find the probability exactly 7 use smartphones. So I just go x equals 7. Compute. And you see it actually reminds me, that's the number lit up, 7, red. That's the probability I want. Can you see the histogram?
Would it be 0.1?
4 decimal places. 0.934.
Okay, you're just taking that one number off. Okay.
I forgot the 0. Okay? So this is pretty easy in a way, getting to understand this, I think. 22. No, 50. 15, question 15. Oh, I'm sorry. Yeah, 23s. Let's see, did I skip one?
No, 23.
That's a smartphone one, same thing. Let's see, is it the same thing? Yeah, it's exactly 9. All right, so here's 54% and N is 8. So 8 smartphone users, and now the percent is 54 instead of 53. At least 5. So that's greater than or equal to 5. Compute. So see, it's lit up 5, 6, 7, and 8. And the total is 4, 5, 3, 7. 4 decimal places. So there's a 45% chance that the 5 of them out of the 8 will be using it. That's what it means. But you see, it applies that formula over and over. It does it automatically.
Yeah.
So that's the beauty of it.
I bet that will be really hard this time.
A survey showed that 73% of adults need correction, eyeglasses, contact surgery for their eyesight. If 18 adults, that's N, and we know P already is 0.73. If 18 are randomly selected, find the probability that no more than one of them needs correction. No more than one would be less than or equal to 1. Right?
Correct.
So it's 0. You know how to read that E minus 9?
I don't actually.
That means move the decimal place. You need 8 zeros in front of that because you move the decimal place over 9 places.
Okay.
That's what it means. Times 10 to the minus 9. That's what that means. Exponent minus 9. But what's the base? 10. So you move it 1, and now you need 8 zeros. So round it off.
Quick question.
Probability 0.
How did they get to 2.8? Is that 2.8 just like at the end of the decimal or end of the?
There you go.
Okay, back. Well, that's the end of the decimal.
Okay.
But it's just such a small fraction. That's where
Okay.
I don't know. If you'd have to calculate it. I'm not interested in doing that.
2.8.
You'd have to calculate that formula twice with x equals 0 and x equals 1 and run through it, calculate it. It did it for us. So it's 0. I mean, it's just not a snowball's chance of that occurring. Don't put your money on it.
If it was E plus 10, would you go right? For
Yeah.
the decimal place?
Yeah. Is 1 a significantly low number?
Yeah.
Yes.
Yeah.
Because the probability of this occurring is small, very small. It's minuscule. It's certainly less than 5%. All right, let's see, that was 27. Based on a poll, 60% of adults believe in reincarnation. Assume that 5 adults are selected. So that's N equals 5 and P equals 60%. What's the probability exactly 4 of them believe in reincarnation? So equals 4. Calculate or compute. Be 0.2592.
Calculating.
It says 3 decimal places. Let's see what happens if I put 4 decimal places.
Wow.
See, it doesn't like it. That's what the computer does too when you take a test. It marks it wrong. If I look and see, and I see it on the test, if you had written the 2 there, I'd give you credit because you were sloppy, but you got the right answer. That's the way I look at it. So unless somebody wants to correct it, what's the probability that all the selected adults believe in reincarnation? So that'll be 5. 0.078. What's the probability at least 4? So you just add them, right? At least 4 means 4 or 5. So you can just add those 2 numbers. Or you can just do greater than or equal to 4 if you're if you have it here, you might as well,
Yeah, 3,700.
337, right? That's the same numbers if you added the two of them, right? 7 and 1, 3, 3. Yeah, if you just add them together. Because that's what you're adding these two columns. If 5 adults are randomly selected, it's 4 a significantly high number.
Yeah. It's 5 adults and,
It's not less than 5%.
yeah, it's 5 adults
It's a significant.
is 4.
No, it's usual. It's a high percentage.
Oh, okay.
But it's not significant. It's not significantly high. It's usual. See, the lower probabilities are down here. The big probabilities are pretty high.
Okay.
So no, because the probability is greater than 5%. Remember, it's the low probabilities that are significant.
Okay.
The high probabilities are what's normal. It's what's usual. I know it's backwards thinking maybe, but that's just how we do it. Number 35. A pharmaceutical company receives large shipments of aspirin tablets. The accepted sampling plan is to randomly, remember we did this before, didn't we? Randomly select and test 51 tablets, so that's N, 51. And then they accept the whole batch if only one or none that doesn't meet the required specification. So that's less than or equal to 1. And all I got to do is change the P. I don't know what P is yet. 4%. So 0.04. So if one or none are defective, then we accept it out of the 51. So that's really a low percentage. 4 decimal places, 3897. 0.3897. Right? Company will accept 38.97%. So how many are they going to reject? They're going to reject 61.03. Look, when you're adding, you just get 9.
Yeah.
Right?
I went.
6 and 3 is 9. 8 and 1 is 9. 0 and 9 is 9. 7 and 3 is 10.
I think do it.
9, 9, 9, 10. Always. That's how we do it. So most of the shipments will be rejected. Almost 2 to 1. Not quite, but almost. But this is a real type thing. That's a pretty high rate of defect. And that's a pretty large sample, 51. So what happens? Do you think that they send it all back? Look, 5,000 aspirin. Oh. Do you think they send the whole shipment back?
Yeah.
It all depends on what they're buying and how useful it is to them. Certain things you need for manufacturing, like roller bearings. If you got bad roller bearings, you don't want to use it.
Yeah.
If you got blemishes on a basketball because the logo was smeared, you might say, well, we'll take them, but you got to lower your price. That's what happens in real life. They make arrangements, depending on what they're buying or.
Okay. But it still works as a basketball.
Yeah.
Bearings aren't going to work.
We'll try another one. Number 36. When purchasing bulk orders of batteries, a toy manufacturer uses this accepted sampling plan. Randomly select and test 43 batteries. So that's N. That's the sample. Determine whether each is within specifications. The entire shipment is accepted if at most 3 batteries. So now we have X less than or equal to 3, and the percentage is 0.01. 1% are defective. See, they already know that they expect, this is what they expect. They expect 1% of those, which is what? 50?
Yes.
So out of those 50, how many will end up with the 43? The probability is 0.9991. right? So now we can say that the company will accept 99.91. How many they're going to reject? 0.09. So most of the shipments, almost all the shipments will be accepted. That's a pretty high number. See, because they have, this company has better quality control. The chances that out of the 43, you get more than 3 is very low. They might even say, well, let's see what happens if you go for 4. Still pretty high. Anyway. You get the idea? Last one, Dan. Okay, well, we've got a couple of reviews. This one is thrown in here. You're going to see this. It's called the geometric distribution. That's the formula. And what it is the first success comes on the last trial. So if you have X trials, then the first X minus 1 are failures. That's because that's 1 minus P is Q. So you take Q to that 1 less, and then P is the first success on it. So that's called the geometric. And all you got to do is put in the numbers. So for this one, let's see, P is 0.13. So we'll take
Wasn't there a geometric calculator on the other guy?
0.13. Now this is easier. Just do it. Now, Q is 0.87 because they have to add up to 1. It's the same idea. And then if there's if the fifth success, then that means there's 4 failures before that.
Okay.
So it's 0.13 to the first power, which we don't bother writing. And so the answer is 0.0745. Okay? You might see that on your homework, or I don't know if it's on a test or what, but if you see it, it's pretty simple. All you got to do is figure out what X is and what P is, and then you can just plug in your calculator. So in this one, you don't need N, you just need X and P. So they said X was 5, so that's why it's to the 4th power. And they said P was 0.13, so that's why you get 0.13, and this is 1 minus 0.13, which is 0.87. So, any questions?
No.
Oh, let me do these couple of review things here real quick. Which of the following is not a requirement for the binomial? Does the probability of success remain the same? Yes. Each trial must have outcomes classified into 2 categories. Yes. The procedure has a fixed number of trials. Yes. The trials must be dependent. No, they must be independent. It's the wrong one. If calculations are time consuming and if the sample size is no more than 5% of the population, which one of these do we use to state that they could be?
Rule of thumb.
No.
5%.
5%. 5% meaning that the sample is less than 5% of the population.
Okay.
Remember that one?
Mm-hmm.
We did it a couple times. Number 3. The binomial probability formula, the variable X represents
Number of trials.
that's N.
Number of successes.
Successes. Because X could be any number between 0 and N.
Mm.
Right? There's no successes or all successes, or anything in between. Okay. And number 5. For the binomial distribution, which formula finds the standard deviation? It's the one I pointed out.
Bottom one.
Bottom one. There you go. You agree? And the last one's number 7. Identify the expression to find the mean of the binomial. Bottom one again. Right. Very good. That top one is is sigma squared. It's the variance for a random, discrete. You can see it's on the other side. But you won't have to calculate that. That's why I didn't really bring it up, because it's, the less, you guys are learning so much new stuff, you don't need extraneous stuff.
I appreciate that.
Yeah, me too. All right, let me stop the